Go ahead.
Good. No. How about now? Yeah. A little bit? Okay. All right, so I'm going to talk about principal symbols, or the generalization of this notion to the non-commutative geometric setting. And so this involves first generalizing a notion of differential operator. And before we can do that, we first have to generalize the notion of jet. So I'll start with jets. And in order to do that, we need, well, two different things. In some cases, we'll just need a first order differential calculus, which has already been discussed in a few talks today, so I won't really harp on that. And in other cases, we'll need the data of an entire exterior algebra. And so I'll mention what that is briefly. So first order calculus, again, we saw this before. An exterior algebra, this is just differential graded algebra, which is generated in degree 0 via the differential and the wedge, where the 0 degree is just some K algebra A. And again, K here, this doesn't need to be a field, it can just be a commutative ring. And if you're given a first order differential calculus, you can always construct a universal exterior algebra, namely this maximal exterior algebra, and any other exterior algebra will just be a quotient of that. So you always do have at least a canonical way to extend it if you're not given an exterior algebra right from the beginning. So if we have an exterior algebra, this is playing the role of forms. What about symmetric forms? Well, we can construct something like this. There's several different definitions one could take, and given sufficient regularity of your exterior algebra, they'll all be the same. This involves flatness of omega 1 and omega 2 as right A modules. And in particular, this will be satisfied if you're working in the setting where everything is finally generated projective. Like, let's say you like quantum groups, everything's finally generated projective. It will in particular be flat. So first, let's view omega n as some endofunctor on the category of left A modules, so just a tensor functor. Then inductively, you can construct these symmetric forms. And I'm kind of hesitant to call them quantum symmetric forms because it doesn't have anything to do with, let's say, quantum groups. But this notion of symmetry can be much more complicated than would be in the classical case, right? If you're in the setting of supercommutative supergeometry and you're in the purely odd setting, then these symmetric forms that you get will be anti-symmetric in the classical sense. So it's some more complicated notion of symmetry. And so the 0 grade of these symmetric forms is just the identity functor. The 1 grade is just this tensor functor with the first order differential calculus. And then after that, we use these kernel functors of this composition here. So in particular, S2 would just be the kernel of the wedge from omega 1, tensor omega 1 to omega 2. And in this case, we're seeing the wedge here as a natural transformation between functors. Everything here will tend to make it as functorial or natural as possible. So once you have a notion of form and symmetric form, one natural thing to consider is the Spencer delta sequence and then Spencer cohomology. So this is originally due to Spencer in the classical setting. And we construct this Spencer delta map, which will for us be a natural transformation. And it's given by the composition of these two maps here. So first we have this map omega k iota n. Iota n is just this map given by definition from our definition of SH. And then you apply the wedge in the appropriate spot as the second map. And there's this -1 to the k here just to ensure we generalize the classical case. And then you get a sequence of endofunctors in this category of left A modules. And it's actually a complex. You can check that it is indeed a complex. And you can consider its cohomology, which we'll call Spencer cohomology. And this will play some role in the exactness of the in getting exactness of the jet sequence later on, once we have started to construct our jets. So let's first look at the one jet. And first, let's do it for the universal calculus, and then we'll do it for some more general calculus. So the universal calculus, we saw this mentioned earlier. This is just the kernel of the multiplication in A tensor A, and it comes with a universal differential. And there's sort of, coming from the classical setting, it's kind of, this A tensor A plays the obvious role of the one jet for A for the universal calculus. And so we define this functor A tensor as the universal one jet functor. And then you can derive this short exact sequence given any left A module E. And we would regard this as the one jet short exact sequence for some module E. And this comes equipped with everything you would want a jet to have, namely this universal one jet projection and universal one jet prolongation. So this prolongation will split this short exact sequence in mod. This is just the category of K modules now. And of course, this pi map here is just this action on the left. But just like we get non-universal differential calculi as quotients of the universal, we can similarly get non-universal one jets as quotients of the universal. By the same thing, actually, namely this ND, so this sub-bimodule. So again, we see any calculus is just some quotient of omega 1u by some sub-bimodule. And Henrik mentioned this morning that in the classical case, if you work locally, it contains things of this form. I think he had a plus here, it should be a minus. So what were you thinking, Henrik? So we can make this functorial as well. This ND, this becomes a functor of first order differential relations. And then we can construct this one jet functor, or if you like, if we work on an actual module, E, the one jet module for E, just as this quotient here. And it inherits a prolongation and a projection from the universal one jet prolongation and projection. Okay. Now, I won't go into detail for constructing the higher jets because we would be here until tomorrow. So I will just sort of say some of the motivation for why we construct them the way we do and what they come equipped with. So they will all be endofunctors on the category of left A modules, and we build them inductively, right? So the zero jet functor will just be the identity, the one jet we just saw, and we will construct higher ones, which all come equipped with natural transformations. This is the prolongation, so a natural transformation from the identity to the n jet, and the projection, so a natural transformation from the n jet to the n-1 jet. And we construct them precisely so that this non-commutative analog of the Spencer sequence, this is closely related to the Spencer delta sequence we saw before. So we construct it precisely so that this sequence is in fact a complex. They're sort of the maximal subfunctors of another jet functor, which I can't really discuss. It would involve more jet theory, but it's sort of the maximal subfunctor of something else, which makes this sequence a complex. And the reason we do this is because we want something that resembles a non-commutative generalization of this geometric theory of PDE of people like Quillen, Spencer, Goldschmidt, Vinogradov, and so on. Another property of jets that you would like to carry over from the classical setting is the jet short exact sequence. And so this would be a sequence of the form down here. So you want symmetric forms, jet, n-1 jet. You want this to be a short exact sequence. You don't get this for free in the non-commutative setting. You need to assume some sort of regularity about your exterior algebra. For the one jet, you automatically get this sequence. For the two jet, you need to assume omega 1d is flat in the category of right A modules. For the three jet, you need omega 1 and omega 2 to be flat. And as you go higher, eventually this will sort of terminate this needing more flatness of omega 1, 2, 3, and so on, these grades of the exterior algebra. You will only need the first three grades to be flat in mod A, but you'll also need this Spencer cohomology, which we saw before, to vanish. And classically, this always vanishes. It's related to, you could say, integrability of the empty differential equation, 0 equals 0, which, I mean, maybe it seems like, of course, that should vanish. But in the non-commutative setting, again, you don't get that for free. This is something you have to check. So once you have jets, now you can talk about differential operators. And just like in the classical setting, you can define them in terms of jets. This is one of the motivation for jets, right? They give you some sort of coordinate-free way to talk about differential operators. So we would define a linear differential operator of order at most n with respect to our exterior algebra as some k-linear map from E to F, which makes this diagram commute, right? So delta is k-linear, this jet prolongation is k-linear, and we require that there exists some left alinear map delta tilde, which makes this diagram commute. And if you remember from the previous slide, if you have the jet short exact sequence, there's a natural inclusion into JNE here of SNE. So you could, if you have the jet's short exact sequence holding, then you can always restrict the lift of the differential operator here to the inclusion of SNE. And this will be related to principal symbols, which we'll talk about shortly. So what are examples of differential operators? All the things that you might hope to be differential operators, at least that we've checked, turn out to be. So the differential D, this is a first order differential operator. If your calculus is parallelizable, so that means free and finitely generated, then there's a notion of partial derivative. These will be differential operators. A left connection, this will be an example of a differential operator. Vector fields, which I'll touch on more at the end, so I won't go into detail here. These turn out to be differential operators. Spencer operators, which I haven't defined in any detail, but they showed up sort of in the motivation. The non-commutative analog of those will also be differential operators. Now, do differential operators behave in this setting as they do classically? Well, at least the first property you might want to check is that you can compose differential operators and again get a differential operator, and will it be of the degree that you expect? Well, if you have a differential operator of order at most n and a differential operator of order at most m, then their composition will again be a differential operator of order at most n plus m. And the way you see this is you consider this diagram here. It involves constructing this map, which we denote L here. Really, the work is just constructing this map L. It's some finite dimensional version of the co-multiplication in the jet comonad, if you're familiar with that in the classical setting. And then you get some category out of this whose objects are the same as those of A mod, and the morphisms are now given by finite order differential operators. Another thing you might want to ask if we're talking about jets and differential operators is, when do jets represent differential operators, which they do in the classical setting, but this isn't necessarily a given in the non-commutative setting. So this is just stating what it means to have a representable functor. So when does this hold? This involves looking at the following natural transformation, which goes from the universal one jet to the n jet. So if we work with some E, so some left A module E, this will take A tensor E to A times the n jet prolongation of E. And we'll need to consider both the kernel and the image of this functor. They'll both play some role for us in looking at representability. So the kernel of this, we'll call this the functor of differential relations of order n. It's sort of a higher degree analog of this functor of differential relations of order 1, which we considered initially. And so similarly, we'll denote this by n superscript n. Now, if the n-jet sequence is at least left exact, you don't even need to assume that it's short exact. But if it's at least left exact, then this natural transformation here, if you restrict it to the n minus first order differential relations, then this map will be valued in the symmetric forms of degree n. And then we have that the following are equivalent. That map being surjective is equivalent to SNE being valued in this left module generated by prolongations of E. And if either of these is satisfied, we'll say that symmetric forms of degree n are generated by differential relations. And this will be very important for getting representability of differential operators by jets. So if you have the n-jet sequences left exact, then and further, you have that the n-1 jet represents differential operators, then the n jet represents differential operators if and only if symmetric forms of degree n are generated by differential relations. And in that case, you actually have that these symmetric forms are a quotient of the n-minus first order differential relations by the nth order differential relations. And classically, this holds, and as far as we're aware, nobody had that perspective classically either, so it's somewhat new even in the classical case. But this only tells you how to go up inductively. We can say a bit more explicitly when this holds. So first we have to introduce this notion, which we call skeletal jet functors. So it's sort of another generalization of classical jet functors. But these are now somehow minimal. They're like the bare bones of what you could possibly regard as a jet functor. It's precisely the thing generated by prolongations. There's nothing else. Namely, it's the image of this natural transformation we considered a few slides previously. And classically, this will coincide with the jets we already constructed. So this is some other generalization of classical jets, but in the noncommutative setting, they do not a priori agree. And if you want everything that you could want from jets classically, in the noncommutative setting, you would need to check that these coincide with the jets we already constructed. So the zero jet obviously agrees with the 0 degree skeletal jet. This is just the identity functor in both cases. The one jet will always agree with the skeletal one jet. But then as soon as you get to degree 2, the jet will only agree with the skeletal 2 jet if first you have this Tor condition satisfied. So in particular, you need either E to be flat as a left A module or omega 1 to be flat as a right A module. And then beyond that, you also need that your exterior algebra is the maximal exterior algebra, at least up to degree 2. Beyond that, we can't say more, but this is perhaps one motivation why it's useful to consider the maximal exterior algebra. It gives you this representability of differential operators by jets. And then we can say that differential operators are represented by our jet functors if and only if our jets agree with the skeletal jets. So if and only if jets are generated by prolongations. So now I can talk about what was actually in the title of the talk, principal symbols. This isn't so much of a result on its own. They're more of a technical tool that you can use to analyze differential operators, right? Like in the classical setting, if you're talking about second order differential operators, you would say a second order differential operator is elliptic if the principal symbol is a Riemannian metric. And if the principal symbol is a Lorentzian metric, then you would say your differential operator is hyperbolic. So this is relevant in terms of characterizing differential operators. And later on, we'll see how it's tied to a notion of Lie bracket as well. So if you have E and F, two left A modules, we can define this space of symbols of order n as just this quotient space here. So differential operators of order at most n, modulo differential operators of order at most n-1. So think of this as taking a differential operator to its highest order term, which sort of governs the behavior of the differential operator to a large degree. Then if E equals F, then this graded K algebra, well, we get a graded K algebra, sim EE, with respect to composition. And how do you compose symbols? Well, you lift them to differential operators, compose the differential operators, and take the symbol of that differential operator. And this is the composition of the original symbols. And you can say more about sim A, namely it's a graded A algebra. And the sim A, classically, this is a commutative algebra. So diff bullet AA is non-commutative even in the classical case, but sim AA is commutative in the classical case. And in this setting, there's a sense it's hard to make it more explicit without going into a lot of details, but sim AA is non-commutative in roughly the same way that A is non-commutative. But I can't really say much about that without going into at least a bit more detail. So this you could think of as sort of a quotient notion of symbol. There's also sort of a restriction notion of symbol, which they both agree in the classical case, but here they tend to be different in general. So if SND is generated by differential relations in the sense that we saw earlier, then we get a well-defined map from SIMB EF to AHOM SNEF. And if the jet sequence is right exact, then R is injective. If this second one is not so important for what we're discussing, so I'll skip that. But what's important here is that if R is injective, we can identify the symbol of a differential operator with the jet lift restrictions to SNDE. And so this is the way you would tend to view things in the classical setting. Like what I said before, if you have some elliptic differential operator, degree 2, then its symbol is a Riemannian metric. You would see it from this perspective, this map from SNE to F. So it's useful to have this perspective, and it's sort of related to the short exact sequence, the jet short exact sequence we saw before. Okay, so why would you want to have symbols? What's another use? One would be constructing a notion of Lie bracket in the non-commutative setting. And so if we want to do that, let's briefly talk about what vector fields would be, at least from our perspective in non-commutative geometry. So for us, this would be a differential operator of order at most 1 from A to A, which also annihilates the kernel of D. So classically, the kernel of D, this contains things like locally constant functions. And this is a bimodule if you equip it with these two actions that we have here. And with these two actions, it actually agrees, there's a bijection between this and the existing notion of left vector field in this setting. And so let's say if the existing notion is reasonable, this one is just as reasonable. It's just a different perspective on vector fields. But now they're things that you can easily compose because they're just differential operators from A to A, which satisfy some other property. Now there's a natural pairing between omega 1D and vector fields, and this is what we're denoting with this angled bracket here. And since our vector fields are a bimodule, you can take their tensor product. And then we have this double angled bracket here, which pairs tensor one forms with vector fields, tensor vector fields. And this pairing is given as you see here. Now, if we want to get some sort of bracket, we consider this diagram here. So here I have vector fields, tensor vector fields. Right? This is just the tensor over K. Now I can pass to the tensor over A if I want. I can also consider the composition map. This should be a tensor right here, not just a times. But so the pairing that we just discussed gives us a map here. This is just the restriction since S2 sits inside omega 1 tensor omega 1. This is the symbol map we considered before. The annihilator of S2, this is somewhat obvious. The only space we really need to construct here is this asim. This is just the pullback here. So this is just the pre-image of the annihilator of S2 under this tensor map. And you can basically think of this as vector fields, wedge vector fields, if you like. So antisymmetric or asymmetric vector fields. And if you take two vector fields, X and Y, and you compose them, they're each first order differential operators. This will be a second order differential operator in general. Now, classically, when you take X composed with Y minus Y composed with X, you're taking a second order differential operator and a second order differential operator. And when you're subtracting them, you're making their second order symbol cancel out. So the second order symbol of X composed with Y and the second order symbol of Y composed with X agree. And so when you take this linear combination, you make the second order symbol vanish. So this is one way of seeing that the Lie bracket of two vector fields is again going to be a vector field. So here, if we have two vector fields and we just take them immediately to their composition, this will be some second order differential operator. But if we start with something here in asim, and we include it in here and then apply the composition map, its second order symbol will be 0. So it will be a differential operator of order at most 1. And you can also show that it will annihilate the kernel of D. So it will again be a vector field. So if you want to get some sort of Lie bracket, what you really want to do is construct some map, or hopefully you have some canonical map, which goes from vector fields, tensor vector fields, to this space asim. So you would have a map which goes here, and then you can just include it and apply this composition map, and you'll get a vector field out of it. So at least you'll get some sort of binary operation which closes. You might not have any other symmetry properties like you would expect from a Lie algebra or from a Lie bracket classically, like Jacobi or antisymmetry and so on. This would come from your algebra and your calculus and other data that you might have around. So let's conclude here by looking at what would a Lie bracket be in this setting. So if you have some k-linear map from vector fields, tensor vector fields to this space asim we saw in the previous slide, then we would call a Lie bracket a map of the form given here. So first there's a flip, which is sort of here for technical reasons, and then you would apply this k-linear map from vector fields, tensor vector fields to asim, and then you would take this composition, and there's also another flip built into the composition. And so really what it seems like you're looking for is some canonical map from vector fields, tensor vector fields to asim. And so examples where you have this is how you get the commutator in differential geometry, the supercommutator in supercommutative supergeometry, and other examples we've looked at are Clifford algebras and finite group algebras. Here you have some canonical invariant inner product, which gives rise to an orthogonal projector from vector fields, tensor vector fields to asim, and from this you can get a canonical bracket in this sense. And then we're also talking to people like Thomas Weber and Paolo Maschiri, who are both here, about trying to get, really it's about getting an example of this map P here for quasi-triangular Hopf algebras. And I guess I'll wrap up there.
According to if you look, is any second order differential operator some of the
So we're not really sure of this yet. Somebody else asked us the same thing, which this essentially amounts to is any differential operator, a non-holonomic differential operator. Is there a difference between holonomic and non-holonomic differential operators? And this isn't necessarily clear. So I would say it's hard to say at this point.
So are there nice cases where you get contact produces
I don't know. I haven't really thought about it from this perspective before. Mauro or Henrik, by the review. Mm-hmm. Yes, exactly. Oh yeah, maybe I should go back to the page where there's examples. So for the differential, let's say the differential is like from so for connections, it's just the identity. The symbol of the connection is the identity. The symbol of the differential from omega k to omega k plus 1 is just the wedge. Spencer operators, it's some combination of the wedge and the jet projection. Vector fields, so essentially the symbol of a vector field in our sense is just the corresponding map in here. Yes, yeah. But these, I mean, these are all first order differential operators. So first order differential operators behave almost exactly like in the classical case. It's only once you go higher that it's not as well behaved potentially.